There you go. All right. With that said, Luis, take it away.
Hey, thank you. Hi, my name is Luis Gutierrez. I'm a software engineer at Microsoft. And I'm here today to talk to you guys about microservices. In particular, what I call Microservices 101, which would serve as a primer on microservices development. Now, if at any point you have any questions or something, feel free to interrupt or raise your hand or whatever. So my goal here today is to try to make a topic as honestly complex as microservices and turn it into bite-sized pieces that anyone can understand. So in here, we're going to start with discussing what are microservices, what are they good for, where should I use microservices, where should I run away from microservices. That we're going to start looking into how to turn an application from what we call a monolith into isolated microservices and have them work together. We will also start talking about how to design microservices. Afterwards, we're going to give a quick pass over the software development process and how does incorporating microservices affects the way we do things. And afterwards, it's going to be an open forum for questions and additional discussion. So, about me, I've been a software engineer for pretty much 8 years. I'm also a certified Scrum Master. I'm currently working at Microsoft as a software engineer 2 for the O365 team. I previously worked for Oracle in the it was invoice management team, and before that in General Electric as part of the tech support team. I also worked throughout my career in different tech-related business ventures. So I can say I am familiar with the software design process from inception to delivery. I've done quite a those in my time. So, and well, I would also say I am the random facts guy at parties, though I don't usually get invited to parties, so that's a random fact, I guess. Anyway, so let's begin here. Any of you have heard before the word microservices or microservice architecture, something like that? Anyone has any idea of what would that mean?
Yes, sort of.
So what's your understanding of what microservices are?
My understanding of what microservices are is vaguely familiar or vaguely compared to like the idea of making modules or libraries for apps. So rather than having all the code in one spot, you split the code into pieces that can kind of be used independently and then run them that way so that they're easy to contain and easy to test, things of that nature, and easy to be reused in other places.
You actually have a very good idea of what a microservices is. The libraries analogy is actually a pretty good one. Anyone else has a different idea on what microservices might be?
So the microservices run on their own process, like small, like threads or something.
Yes and no. They are not necessarily a single process. They can actually involve several processes working together on a single machine. You can think of them as self-contained small applications. So, okay.
So is there any core like number of cores limit for running microservices, like the CPU cores?
Not really. If your service is lightweight enough, or for example, it's optimized enough, you can actually manage in a single computer. So it depends mostly on what are your architectural constraints, what is your audience, and especially how much budget do you have at the end of the day, because if you want to scale up, you will need additional servers. But well, that's a fact of life at this point in time. So I hope that one answered your question.
Yeah.
Okay, so microservices can be summed up pretty much in this small phrase. A microservice architecture consists on developing simple, small, decoupled services and connecting them together into a single cohesive application. What does this mean? When we're talking about microservices, we're considering an application to be conformed of different little pieces. These separate pieces may represent, for example, business areas or parts in a process pipeline or specific resources. In this case, the way you can decompose a single application into microservices depends on what exactly are you trying to achieve with this. We will get to this point later. But in essence, you break down an application into simpler services and tie them together by means of intra-service communication. So for an application to be composed of microservices, each service must comply with three particular characteristics. They must be specific, they must be self-contained, and they must be loosely coupled. Now, what does this mean? For a service to be specific, it must perform a distinct set of responsibilities. For example, if you have an order microservice, it is the only item in your application that is allowed to work with orders. Likewise, if you have an invoicing microservice, that's the only thing that can work with invoices. It doesn't mean that it is that other services can't rely on that information, but it means that all the important operations to perform on that particular resource or process are done by that service exclusively. Now, self-contained goes in hand with the specific constraint. It means that all related behaviors stick together. So if we have a service which operates on, for example, movies, everything related to those movies should stick together into the same service. And this can include, for example, movies, movie recommendations, actor listing, producer listing, and whatnot. That information makes up what a movie is and thus belongs to the same service. Likewise, any operations like, for example, searching for movies, searching for producers or so, they should belong into a single service. Again, this definition allows for you to split things into a more granular level depending on your specific needs, but we can consider this like one of the main characteristics. Finally, what does it mean for a service to be loosely coupled? It means that within the cluster of microservices that I have, which collectively are referred to as the service mesh, I can grab any single microservice, replace it with another, or upgrade it independently of everything else, and everything will still be working. Unless, of course, I break it with my changes. So in that sense, microservices are a collection of services which share these three characteristics and which work together to achieve a certain outcome, which in this case we collectively know as an application. So up to here, any questions? Okay.
Hey, I do have one question for you,
Yeah.
Luis. What is that beeping in the background?
If you hear something beeping on my end, it's probably my 3D printer. So let me play with my microphone here a little bit.
That's good. It's okay.
Yeah.
But it sounds like you're talking to us from the hospital or something. It's a very consistent beep.
Yeah, it's
so how do you feel about the idea of this microservices architecture being something that's useful for more than just like backend services? This seems like a pretty good strategy or a healthy strategy for lots of different types of development.
And you'd be right, actually. They are mainly used for backend services because our day-to-day applications are becoming complex enough for they to require this kind of layout. Because one of the interesting side effects of microservices, which I'll jump right now, is that they allow you to get more fine-grained control over the immense complexity of your application. So the more complex your application is, the more sense it makes for you to turn it into microservices. Why? Because in that way, each independent service will be can be managed by a single team. You don't really need like an entire department devoted to maintaining an application. You can have smaller, more nimble teams managing an aspect of the application and working together to achieve the same outcome. There is this concept, I don't actually remember the name of the guy who coined it, but it says software tends to imitate your business structure, and your business structure adapts to what your software demands. So when you are moving to microservices, you can expect your business structure to become like little tiny teams working together to achieve something. And that is actually a good thing. This allows you to grow your application in a sustainable manner, as well as growing your team in a way that doesn't imply chaos, especially for middle management. So another advantage of microservices is that, well, because we are no longer dealing with the entire pie, but just a single slice of it, we can anyone coming to the project can understand what's going on faster because it's a smaller code base. And once they do understand it, it makes your development process faster. You can get more things done faster, and you can, for example, build your project faster, get it deployed faster. It helps you keep things controllable. Now, another perk of microservices, and this might actually go hand in hand to the last question, and that is that microservices give you a lot of flexibility. And it's flexibility not only to what kind of things you can include, but how these things are built. For example, if you have a service which requires a highly optimized code for a critical section that needs to operate in millisecond range, you can easily implement that one in, for example, Go, Rust, C++, if you like that kind of stuff, and have it coexist with, for example, Java code, Python code, JavaScript code, or whatever else you might need. You can actually have a polyglot implementation for your service. In this case, it boils down to picking the right tool for the right job. And microservices actually allow this, because for each individual service, it doesn't matter if the other one is implemented in something different, as long as they can talk to each other. And that's like one of the cool things of microservices. You can use the right tool to solve your problem in the most effective fashion without being stuck to a specific set of tools. You can also scale it depending on your current needs. For example, earlier we were discussing about it was movie streaming, I believe. If you have a monolith-based application, scaling that would require you to deploy entire servers to deploy your application. And well, if it is a monolith, it implies the application is generally large. So it will take longer to load. You will need a larger database. You will need more resources. That is not the case with microservices. Since microservices is a flexible mesh, you can actually scale things individually. So for example, if you are currently experiencing a service peak because everyone is trying to download the latest music album or whatever, you scale up the part of your application that handles that specific function, keeping the other ones at a bare minimum if that's what you need at the moment. This allows you not only to control costs and resources, but also it allows you to create resilient, adaptable applications which are performant in pretty much every situation. Now, despite all of these advantages, microservices do have a couple of things going against them. One of them is that once you start going down the microservices rabbit hole, you might find that suddenly it starts to look like a good idea to create a microservice for X particular function, or now that you have that one, then you suddenly realize you need Y, Z, and W functions and whatever and whatnot. And suddenly you end up with a bazillion services which pretty much do nothing and cost a lot to maintain. So without the proper team discipline and the proper management discipline, having microservices can actually become something of a Pandora's box. Once open, it's havoc. So it requires from management as well as from each individual team a level of discipline not normally found in a software project, especially a monolithic project. Why? Because since each service now serves a particular functionality, you are now obligated to well, the team that handles that microservice is now obligated to look through the entire life cycle of the service. This means from planning new features, implementing them, testing them, releasing them, and then checking everything is in working order in production. Long story short, your team becomes a DevOps team. So this is an expected transition, what that happens when you start incorporating microservices. But if teams are not prepared to do this change, you will encounter a lot of resistance and undesired side effects because of it. Also, another problem with a microservice mesh is that instead of having one single item to concern about, albeit a huge one, we now have hundreds, if not thousands, of little pieces. And you know what happens with little pieces. The more moving parts there are in the system, the easier it is for something to go wrong. So in this case, what we mean with going wrong doesn't necessarily mean, for example, having something crash. This isn't actually that big of a deal in microservices. What we mean with that is that we increase our attack surface in terms of security. So if someone were to try to perform a cybersecurity attack against us, they have a larger surface from which to try to grab onto. So security becomes more important. Also, if boundaries are not correctly defined, we will start getting a entanglement between different functionalities, and then we lose the properties of microservices. One last point before we move to the next slide. Having as we discussed earlier, having microservices means having small services communicating with each other. Communication necessarily implies networks. So if your servers have a pretty restricted networking quota, then microservices may not be for you, because automated services can become quite chatty. So they may exhaust your network resources in the snap. So that's pretty much it regarding to disadvantages of microservices. So any questions until now? Cool. So let's continue. Okay. So this boils down to should I be using microservices for my application? As previously mentioned, microservices are not suitable for every single kind of application. If you're developing a calculator for your phone, perhaps you would not like to have microservices involved at all. But for example, if you're trying to design the next Netflix, the next Google, or whatever, then it starts making more sense. Actually, determining if you require microservices is a little bit more complex. So I actually tried to sum it up in this little chart. So one of the first things you need to take into consideration is when you're getting started with an application from scratch. Generally, trying to do microservices that way ends up in disaster. Anyone can give me an idea of why would that be the case?
Why? Which part would be the case?
Trying to go with microservices when you're just starting the app. When, like, for example, you just created your GitHub repo, you started punching some code. Why would it be counterproductive to try and go the microservices route at this point?
Probably just because of the initial logistics of setting it up. Like when you're optimizing that prematurely, you're going to spend so much time just getting those all connected and running that it's probably not worth it if you're just trying to prove something out.
Yeah, that's one of the important points. The next one is, we already discussed that microservices are complex and they tend to grow complex if not correctly constrained. So if you don't really know what are you building, you will most likely start generating microservices which do nothing or do too much, or in general, they will not be balanced. So you will end up with microservice sprawl and you will eventually have exactly what we discussed previously. A bazillion microservices which cost a lot to maintain and which don't really add value to your application. So for that reason, if you don't know your app, please don't go the microservices route. Understand what you're building, then you can go the microservices route. Then also, once we pass this initial know your application test, the next thing we want to look at is if we have something that makes this transition worth it. For example, do we have multiple non-related features, pipelines, or or sections in your app that can become independent without compromising the integrity of your application? Or, for example, do you have any architectural constraints, like, for example, we need 4 nines availability, or we need to be able to scale on demand, or we need to have ultimate performance or something? If those are your architectural constraints, then it might make sense for you to go down the rabbit hole and implement microservices straight away. Also, if you have something already built which matches any of these criteria, you can also go ahead and break it down into microservices. Otherwise, it's not really recommended, because you're, at the end of the day, you're investing man hours, time, and potentially money into making a change that may not be worth it. So before actually trying to jump straight into the rabbit hole, analyze your application, and if it makes sense for you, given the kind of work you're doing or the kind of architectural constraints you have, if it makes sense, go with it. Otherwise, hold it back until you have something that makes it worth it. Does this make any sense to you? I figure so. So, yeah, you want to say something, Brandon?
No, I was just going to say, I think it makes good sense to me.
Awesome. So, one of the core things we should remember about microservices is that microservices are not the end goal. Microservices are a tool to reach your application's goals. If you create an application using microservices just for the sake of it, it's probably not going to end well. As we said, microservices are a journey. You start with an application, a solid concept of an application preferably, and then you start trying to see, okay, how can I change this so that each element becomes more independent, more scalable, more whatever. It depends on your specific needs, until you end up with a naturally formed microservice mesh. So, by the way, this presentation includes a couple links. I'm gonna share this presentation with you guys at the end, so you can actually access the links. I believe the information I collected on these links will actually help you guys understand a little bit more about microservices, and in general, it will help you get started if you want to try and learn more about this subject. So, now that we've established the good, the bad, and the ugly of microservices, let's say, okay, we've now seen this, we're convinced we actually need it, so how do we get started? That's a pretty good question. So, when we get started, we have two different options. We either start from scratch, in which case we will need to jump straight into design phase, or we have something, which will most likely be the case. If we do have something, we need to go through a process we in the microservices world affectionately call breaking down the monolith. What does this mean? It means extracting the different services from the monolith and essentially breaking it down until everything becomes a service mesh. So what do you need to start breaking down the monolith? I would sum it up in two different things. Knowing the big picture, in this case, understanding the application, how the different pipelines the application runs, the different core areas it has, the different resources it operates on, And with that knowledge, identify behavioral or functional seams in the code, which you can use to split out items. So what is a behavioral seam? Does anyone have any idea of what do I mean with a behavioral or functional seam? No one? Okay. So a behavioral or a functional seam are boundaries in the code base. These boundaries are mostly logical, though you can sometimes see them manifest in the way your application is structured. These seams are code-based points in which something changes, something in your general architecture or in your general design, your general application design. This can be, for example, a business area. For example, one module works with accounting, another module works with inventory, that kind of stuff. So those we can trace down to individual business areas. Those are good candidates for seams. Also, another interesting area in which you can find seams is through capabilities. For example, user authentication, monitoring, profiling, that kind of stuff. You can actually use those capabilities change to break down your application. Finally, we have process seams, which include, for example, the different stages within a process pipeline. For example, the different stages in an online shopping application, from adding stuff to your cart to the ultimate checkout and payment. That one is a process, and it can be discretely broken down into steps, which individually can potentially become microservices by themselves. Every time you detect a change in one of these areas, you are most likely seeing a behavioral or functional seam. And that is an excellent candidate for you to go ahead and chip it out of the monolith. Now, breaking a seam from a monolith is more or less like a surgery. It must be done with care, it must be done with precision, and if you can have it automated, it's better for you. Why? Because when breaking stuff out, you might invariably cause something to go amiss with the remainder. So if we, for example, extract the orders part from our monolith, we might end up with weird conditions, especially since monoliths tend to get a little entangled within itself. So you need to do this one step at a time, going carefully, separating everything. And once everything is correctly separated, then you can call your service released. Now, I won't go into many details on how to actually perform the breakdown. In this case, I am adding here a very comprehensive set of recommendations by Martin Fowler, which you can later go into and check for additional details. What I will mention, though, is recommendations on how to select what to break down next. In this case, when we are analyzing our monolith to determine what we want to extract next, we would prefer to guide ourselves with these 5 criteria. A change of pace, which means is this area currently under development or not? If it is, how much development is it getting? Because a code area which is actively getting love from developers is more likely to withstand the extraction. If we are working with like code, with some code that hasn't been touched in a lot of time, chances are you're going to have a very hard time identifying if anything goes wrong. Also, we have team structure. What we mean with team structure in this case is how is the team that owns the monolith structured within? For example, do we have a team, a subset of the team which is already taking, which is already in charge of this particular section I am trying to break down? Yes or no? If we do, that something will eventually become the owners of the new service. So you want to have at least a small team of people already knowledgeable in the code you're working on to be able to take it out, make it independent, and handing it over. Then entanglement. As we mentioned before, monoliths tend to become these giant spaghetti monsters we all know and love. So in order for us to break down a monolith, we need to look out for the place in which it is the less tangled. And with tangled, we mean the section of the code with the least amount of dependencies. Dependencies within the code. If we're not talking about, for example, third-party libraries or whatever, it's only dependencies between the code. For example, if code section A is being used by B, C, and D, but D isn't used by anyone else, then D is a good candidate for extraction. A, definitely not. The good thing is the more services you're able to extract from the monolith, the less dependencies there will be. So it will eventually become easier to find and separate things. Lastly, we have security concerns. If there is like some genuine business or security reason for which some item should be extracted or its counterpart kept in for the time being, well, those reasons should be respected. And at last, we have the tech stack. If you're dealing with your legacy COBOL code or something, it's probably a good idea not to touch it at this moment. The newer the code is, the newer the tech stack is, the more likely you will be able to extract it successfully. Now, we've only talked about how to separate code, but our applications are rarely just a code. We usually have stuff like, I don't know, databases or monitoring tools, that kind of stuff laying around with our application. So when we start breaking down our monolith into services, those additional tools and support items will also need to be broken down. The most common ones are databases, transactions, if your application does use transactions, and monitoring. So in microservices, each service owns its data. And this means and this generally means a service has its own database from which it will store its information, keep its cache or whatever. Since each service will be in charge of maintaining their own data, all the tables associated with this behavior you're extracting, you want to move them to a new database. Generally, you want to try and break the seams in the database before breaking the seams in the code. And this process will consist in the data migration. You cannot just remove the tables from here, add them here. Yeah, it needs a little bit more finesse, if we can call it that way. So to remove it, what we need to do is copy over the information, migrate everything we want to migrate, dissolve a few foreign keys if we need to. And once we have everything migrated over to the new database, then we can factor out the service. And once the service is standing on its own, we can sever the link by removing the old schemas from the database. Now, I will jump to monitoring because transactions are its own kind of beast. So monitoring in a microservice world implies aggregation. Since you no longer have a single unified application, you now have different chatty services, each reporting back their status. Making sense out of that noise is called report aggregation. We want to have our reports aggregated in some way for us to be able to, at glance, determine what the status of our entire application and its constituents is. Some recommendations for this include aggregating by service calls, aggregating by pipeline, aggregating by event flow if you are using, for example, an event hub or something. These are just recommendations. There are more ways to perform aggregation. These aren't the only ones, but these are like the most used ones in real world microservices. A recommendation at this point would be to keep your log standards, to keep your log format standardized. Why? Because you will, when you're aggregating, you will eventually need to perform some measure of parsing. The more standard your log format is, the easier it will be to parse your logs down the line. And this might not seem like a lot, but once you start working on dashboards and realize your logs are all different and you can't extract the same information from log A and log B, then you will know what I mean. Lastly, transactions. These aren't that big of a deal for the bulk of applications. You will usually see these more with financial kind of stuff because they need to keep everything in lockstep. But if your application is one of the lucky ones, then I got some good news and bad news for you. The good news, you can definitely go to microservices and it will actually help your application. The bad news is something we call the cap theorem. Has anyone ever heard about the cap theorem before?
I have, but please go ahead.
Okay, I'll go ahead. So cap theorem, cap stands for consistency, availability, and partition tolerance. The cap theorem states that in the event of a network partition, in the event that your services become separated by some issues by some issue in the network, for example, a data center going down or whatever, you will have one of two choices. You can keep your service up and running, which will make it available, or you can try to be consistent. If your application requires transactions, you will generally want to be consistent. For the bulk of applications, this isn't really a problem, so the choice would be to head over to the availability realm and try to keep your application running for as long as possible. But if for some element in your application this is not possible, you will have to make the choice. Either you continue to work or you stop what you're doing and try the best you can to remain consistent. If you cannot be consistent, if you want to be consistent, you cannot be available. If you want to be available, you will eventually be consistent, but not right away. That's a trade-off, and that's cap theorem. Any questions until this point? Up to this point? None? Okay. So let's see, what's our time? Whew. I think I'll step up the pace a little bit. Okay, so designing for microservices. Once you have your once you start breaking down your monolith, or once you start designing your application, you will need to take additional considerations, because at the end of the day, microservices are a subspecies of what we know as distributed systems. So since we're no longer talking about a single process, a single machine, a single data center, we need to take additional design considerations in mind. So we will go through the most common ones of them. I can assure you there are many, many others, but we have limited time, so let's get right to it. Okay. So one of the main points of microservices is having little services communicate with each other. We achieve communication by using a standard language agnostic, technology agnostic solution. For example, we can have services communicating through JSON plus a REST API over HTTP. We can have our servers communicate through protobuf plus gRPC, or if we want to sound a little bit more obsolete or whatever, we can use XML plus AMQP broker. The choices, we have a lot of them. These are just like a little sampler of them. So once we establish what's our communication channel, we need to establish how are we gonna talk to each other. If I for example, started talking to someone else in a language they do not understand, I believe we're not gonna make a lot of progress. So having a shared understanding is key. And in the realm of microservices, this shared understanding is achieved through shared models. Shared models, we can consider them as, for example, JSON schemas or XML schema definitions, or buffer messages, that kind of stuff. It's a standardized way to represent your information in transit between one service and another. This allows our services to be able to communicate with each other. They can send each other messages using our shared models, and they will all know how to interpret each message into an item. They know what does it mean, what it contains, and what to expect from it. Now, there is a little gotcha regarding shared models, and this is they are shared. If you modify something about a shared model, this will have a cascading impact over a lot of places. You can't just go ahead and modify your model A because it so happens that services B, C, D, E, F actually use that model. So you will need to go in and refactor services B, C, D, E, F. So while we are designing this and while we are implementing features atop of our applications, our shared models are best understood and best used as immutable definitions. This means the definitions, once set and once in use, never change. This has implications in the way we design and think of our APIs, which we will cover later down the road. But at this point, if you take something out of it, is shared models are immutable. You don't simply modify your shared models. Now, one last topic before moving to the next design consideration. When we're talking about communication channels and communication modes, we have two big areas which we two big styles of communication we can use. We can either have synchronous communication, which if I can relate it to something we can see in our day-to-day lives, it would be equal to your standard Java code or your standard C code or whatever. It's fully imperative. It states what must happen at which point and what responses do you need to get. And if you don't have the response, you can't move forward. So synchronous communication directs the order in which actions must take place. A happens before B and B happens before C. The opposite to this is asynchronous communication. Asynchronous communication merely states what you want to achieve. You state the actions that must take place during your process, but you don't enforce a specific order onto them. So if your service requires actions A, B, and C, that's about it. They might end up like ABC or CAB or BAC or whatever combination of the above. It doesn't matter. So if we can compare it to something we might all be familiar to, this is more akin to SQL. In SQL, you state what do you want to see. It is up to the database to make sense of whatever you're asking it to get and making it happen. The only thing you are actually doing is stating your intention. You say, I want to see X, Y, and Z with these properties. In asynchronous communication, you say, for this step to happen, these other things must happen. When? I don't know. I don't care. They just need to happen eventually. So when asynchronous communication makes sense when we're talking about, for example, message passing or non-strict pipelines. They work best when used as intra-service messaging, unless we require some degree of consistency, in which case we will resort to synchronous communication. When we are communicating with our clients, for example, our web pages or our mobile applications, it is best for us to use synchronous communication every single time. Now, one of the perks of microservices, as we mentioned before, is microservices are, they own their data. Each service has its own database, its own set of resources that it has in hand. This is actually good for the service itself, but generally information is something that exists in a vacuum. Generally, if we have like an orders table, it doesn't really make sense if we don't have some sort of inventory to back up the order. And thus, we need to share information across services. The moment we need to share information, we need to establish communication. And as we discussed before, services can actually get pretty chatty. So it is generally a good idea to keep a cached copy of everything you query for. That way you minimize the amount, the impact over your network bandwidth. This, however, has a rather inconvenient side effect, and that is all the data we have in cache has a time to live, a TTL. Depending on how much TTL you have available, your data can become stale or it can become obsolete. So it becomes important for you to not only keep a record of when did you get the data for the last time, but also you need to keep a good cache eviction policy, and you should be able to refresh the data when it becomes stale enough for you to consider it useless for whatever you're doing. Now, quick parenthesis in that point. Remember CAP theorem? CAP theorem affects even internal communications. So we can never assume networks are reliable. Most probably the local host is unreliable at times. So they can and they will fail eventually. Maybe not now, maybe in a month or so, but they will fail. So when you're designing stuff, you need to take you need to think, if I am unable to refresh this bit of information, can I work with this for longer? Which means, can I have semi-fresh or semi-stale information going around my system? Or if I really need it to be super fresh, super up to date, then my choices go down significantly. We can either keep operating with stale information or no data at all. It's either you become available or you become consistent. No other choice. So depending on your information, and that depends on, well, what you have what your needs are for your application, you'll need to choose either one of the other. Any questions so far? Okay.
Yes. What did you say TTL stands for again?
Time to TTL means time to live.
Time to what?
Time to live.
To leave?
Live, L-I-V-E.
To live.
Time to live.
And to live.
Yeah, to live. Yeah.
Like life. So
Exactly.
basically, if I recall correctly, is every package, network package, has a longevity. Otherwise, it should be discarded, right?
Oh,
Exactly. Every data element you have in your application has a time to live. So some of them may last for a couple minutes or so. Some of them can last for months. It depends on your data and how much and how fresh you need it for whatever your purposes are. So there is no like guideline on, if your data meets these criteria, then its TTL is X. There is no such thing. It depends on your application. Because, yeah, go ahead.
Yeah, I was gonna say, because one example of this is there's data that is constantly being mutated, right? And there's data that rarely changes. So I believe the other day you were mentioning that a user profile rarely changes in an application. Like once you said your name, your username, your password, your phone number, the user rarely is gonna go back and change it. So if you're caching that data, it's gonna have a larger time to live. But there's other types of data that can change frequently if you're doing transactions or of the sort.
Precisely. And that's the main point about data lifetimes. If you're able to understand how long does your data, how long can your data survive without it being refreshed, the better. And that depends entirely on how you use the data. Well, any more questions? No? Okay, let's move on. Now, client interaction. What do I mean with clients? Any ideas? Please don't read the content. Okay. Clients include, for example, mobile applications, web pages, desktop applications, IoT devices, even other applications which use your public API. those are clients. Clients allow a user, or they act in behalf of a user to interact with your system. Now, when we move to a microservice mesh, we can't really expose the client directly to the microservices, because what happens is similar to what would happen to you if you were chatting with 10 different people and everyone was talking to you at the same time. You will not be able to understand anything of what they're saying. So it will be pretty much the same situation for your client. Your client needs a unique, standardized way to access all the chaos within your service mesh. We achieve this through what we call a gateway. The gateway is pretty much an API aggregator. It collects all the different functionalities your application provides and exposes them in a standardized fashion. A good example of this is, for example, a public API to any big service, for example, on GitHub's public API or Facebook's public API or whatever. Those ones are actually implemented as gateways. Now, one thing we should consider when designing gateways is the more capable your client platform is, the more features you can expose to it, and the more flexibility it will have to access those features. And I know you guys will agree with me. It is not the same to create a web application than creating a mobile application, than creating a desktop application. It's not the same. The capabilities are different. One has more computing power than the other. One of them has more restrictions because of security concerns. I mean, the web browser, for example. Other devices might be very memory and resource constrained, like, for example, IoT devices. So our gateways should match the capabilities of whatever we are interacting with. And I say should as in it would be nice if you, not as something imperative, because at the end of the day, having a general purpose gateway, or a gateway which exposes all the functionality to all your clients, in some scenarios it can be advantageous. However, the main drawbacks of a general purpose gateway is it's a larger attack surface. It exposes unneeded functionality, and it also adds additional strength to your service mesh. You will need additional resources to keep it up and to maintain it and so on. So an alternative to generating a single general purpose gateway is what we call a backend for frontend. A backend for frontend is a smaller gateway for a specific breed of clients, which these kind of gateways only expose the minimum required resources for that client to work with them. For example, if we're working on an IoT device, we don't really want to forward them massive amounts of information. We want to dose it bit by bit so we don't actually saturate the poor thing. Likewise, if we're working with mobile applications, we need to send compact payloads because network resources, especially when we're using mobile data, they can become quite scarce. That is not the same case with, for example, a desktop client or something which has the computing power to absorb massive bursts of information. So the purpose of having a backend for frontend is to create specially designed gateways matching your client's expected capabilities. This also has the nice perk that it allows you to save up on resources. So you don't have to buy a beefy server in order for you to work with it, unless you really have to. Another alternative for this one is having what I refer to as a flexible gateway. Flexible gateways are like a hybrid between the two. You have a single gateway which aggregates every single resource. However, it does not expose every single resource. You generally use a DSL or something to query for what your client needs. In this case, you have your gateway. It consists on a query service which, given the query written on a DSL, requests enough information to fulfill that and sends it through. One of the most popular choices, and as far as I'm concerned, like one of the only choices around, is GraphQL. I don't know if anyone is familiar with that technology, GraphQL. Anyone?
I've been looking into GraphQL, but it's not a thing I would be confident working with yet. But I know it's very flexible, where you make like a query and you basically obtain the data that you need through like a query on the client side.
Indeed, it is actually quite flexible. The only concern we could have with that one, if we can call it a concern, is that it requires an additional service which we must maintain, because at the end of the day, we need to add a query service for it to receive the incoming query, parse it, request information, and fulfill it. So we can actually say it comes up separate to the actual gateway. So it adds additional burdens for us to maintain. Also, having a very flexible client opens up our attack surface. So that's something we also want to keep in mind when making our choice. Gateways are our topmost layer. So every client will be interacting with it. The larger it is, the more likely a rogue client might be able to exploit some or all of our gateway in order to get access to our microservices. So security, especially on the gateway layer, is a bit more involved. I won't get into many details because, well, sadly I am not a security expert. But one of the main points with it is when designing a gateway, make sure you expose as little as possible. Okay. Next point. Remember at the beginning when I mentioned share models are meant to be immutable? When we say something is immutable, it means it cannot change. And this actually has several implications for us. Because if something cannot change, how are we supposed to evolve it? How are we supposed to grow it or provide new services if we cannot modify what's already there? Well, fear not, because immutable is just another kind of mutable. So what happens when we have immutable information is we generally work with a different paradigm. We can just go ahead and make direct changes to it because we will be causing issues. So here is where versioning comes in. When we version stuff, we essentially create different instances of that thing. For example, we can have version 1, which has some characteristics, version 2, which has additional characteristics, version 3, which does something else, and so on. Now, when one of the challenges when working with versioning is something that we can call version drift. And version drift occurs when two different things grow or are updated at different paces. So if we have a model which, if we have two models and one is on version 1 and the other is on version 1, but then we bump one of the second one to version 2, now we have version drift. There is a difference between the versions of each item. This is not necessarily a bad thing. It's something that we need to consider. Now, what does this have to do with anything around here? Yes, version drift is acceptable as long as everything is consistent. As long as we are not messing up with the shared models, our service mesh will continue to operate. So we're pretty much back to square one. How can we modify something that cannot be modified? The main point I want you to take about this is when dealing with shared stuff, avoid the temptation of changing it. The way we change immutable stuff is by creating a new version and gradually phasing out the old version. How do we achieve this? The only way to remove an immutable thing is to stop using it. You phase it out. So there are two strategies for this. One of them might sound more familiar to you. Maybe you've seen it in your day job or something. But it's good to know that more than one alternative exists. The first one, and I would think the most simplistic of them, is the progressive migration strategy. Within the progressive migration, we create the new model, the new version of the model, and we start the deprecation process on the old one, in which we say, we will support this model until this date. At this point, we will drop the model and everything related to that model will cease to function. So all our clients have until this date to make their changes. That's the progressive migration. We go by means of a deprecation strategy, of a deprecation period, sorry, to give our clients time to drop the old model and start using the new one before we actually make the cut. When we make the cut, we simply stop using the model and everything goes on. And we all go along with our lives. Then we have something called the concurrent migration. In a concurrent migration, we don't establish harsh limits. We use a more, I would call it, gentle approach to migrating stuff. So when we say we have a concurrent migration, we have two different versions of the same model or the same API coexisting at a given time. The way we make a transition with this kind of model is to slowly redirecting usage from one point to the other. Once everything is migrated to, once the majority of traffic is going to the new one, then the new one becomes the new standard and the other one becomes abandoned. This has a nice perk because since we are not removing it entirely by means of the deprecation, if there is something going sideways with our new implementation, we can easily roll back by means of a feature switch or whatever. So a couple of these, this kind of strategy is especially good when we're using a blue-green deployment or a canary release strategy, because these kinds of deployments are especially geared to this kind of slow-paced release cycle in which we can have more than one version coexisting at the same time without imposing like a fixed schedules on each bit of information. Now, at this point, does anyone have any questions?
What is a blue-green deployment?
Okay, blue-green deployment consists of the following. The best way I can describe it is we have two different versions of our end environment. In this case, we shall call it prod. One is the blue deployment, the other one is the green deployment. The idea of these ones is one of them will be the stable version. The stable version will have all the characteristics of a good prod deployment. Everything works, stable, everything is stable most of the time. No big changes occur over this side. It is generally what you can rely on. The green side, however, is where magic happens, because this one is not directly visible to your production traffic, although it exists as a copy of the of our stable prod deployment. In here, we can go a little wild, introduce new stuff, introduce breaking changes or whatever into that one. The idea with the blue-green deployment is once we have enough features in the green deployment, we start redirecting a little bit of traffic from the blue deployment to the green deployment. Then we increase the amount of traffic we direct. If everything remains stable, we increase it, we increase it, we increase it until we reach a point in which the green deployment has all the traffic and the blue deployment has none of it. Then our former blue deployment becomes our new green deployment, and the green deployment becomes our new stable blue deployment. Does that make any sense?
Yes. Yeah, thanks.
Awesome. A canary release is actually quite similar. However, canary releases, unlike blue-green deployments, are opt-in. You might have actually seen them, for example, with pre-release versions of websites or even in the browser. I actually recall, for example, the Chrome browser had a canary release channel in which you could try out the latest features, knowing that it might be buggy and everything might break all of a sudden. So the main difference here is canary releases are opt-in for the clients. They can choose to go and try out the new features before they are released, under the knowledge that everything is not stable. So you use a canary release with this strategy to get some prod traffic and try out your new features. Once you have enough confidence in one of those features, in the features you have on your canary release, you can then bump it to become the prod release. Then you deploy additional stuff on your canary server and the process repeats itself. Okay.
Luis,
Yeah.
so we're running out of time, but I believe we have enough content for a second session. How about we invite you? So how about we leave deployment for a second session?
Okay, sounds good to me. Awesome.
Sounds great.
So before we actually leave, does anyone have any additional questions or something you'd like me to answer before we leave?
I I think the only question I have, Luis, is will we have access to these slides and the links that are available within them as well?
Yeah, that's one of the main goals of having the links in here. I'm gonna share this presentation with you guys. So let me first stop sharing, and I'll contact maybe Eric or you, Brandon, after this session to provide you with the slides so you can have so you can distribute them to everyone who attended.
That's perfect.
Yeah, I actually have access to the slides. If you allow us to share them, we'll be more than glad to share them with anyone interested.
Please go ahead.
All right, sounds great.
Luis, thank you so much, man. That we didn't even make it to the end. That was so information dense and so useful. And maybe, maybe more for me because I'm right in the middle of not making microservices, but trying to split an app into lots of modules. And I feel like a lot of the content in this is very relevant, even if you're, trying to do the mobile app equivalent. So this is, yeah, I love how you called this 101 like this. I feel like there's enough information here for it to be a college class.
Awesome. I'm glad you liked it.
Thank you so much.